Hi, and welcome to this lab. Basically, as I said before, the lab actually instructions are should be self-explanatory. It's only really one activity that you're repeating it time and time again. Basically, each time you're changing the material, meaning you're changing the index of refraction, and you're recording the data, you're drawing, then you're doing the same thing again and again and again and again and again. The number of points on this lab is like 217 points or something like that, and it's repetitive, okay? The point is you have to do it, to do all of the steps so that you can get credit for it, okay? Because I know it's repetitive. Sometimes you have the index of refraction is this value, the first one, the second index of refraction is different, and then you calculate the end, you measure the angles, you plot them, and then you go to the next step and the next step and so on and so forth. It should not really be too long in terms of doing it, but it's kind of tedious, that's all. And you have to pay attention to the details, and don't forget you include the drawings. That's the only thing that is really long on this one. And since this class is really geometrical optics, I think it's very, very important that you guys practice the geometry and draw charts and draw basically, not charts though, geometries in this case. So that's the whole purpose of this lab, so that you can understand Snell's laws for the law of reflection and refraction and how they're impacted by the index of refraction. That's basically in a nutshell how this whole lab is. So let me share the screen. Again, these are the lab instructions. Two basic laws of Snell instructions, Snell's laws, and both of them are actually, we explored them today in chapter 34, both of these two ideas. The first one is the law of reflection, and that gives me the index of, how should I say, the angle of incidence is equal to the angle of reflection, theta A and theta R. And I'm sticking to the notation of the book because the book has theta A and theta R, theta B for the incidence and the refraction, and has theta R for the reflection. Okay, so this is basically, you have two indices of refraction in here, N1 and N2. We're going to discuss also the total reflection in here in this case. So this is the second Snell's law. This is the first one. When you have a monochromatic, non-monochromatic light, basically like white light going through a prism, it's broken down into different frequencies in this case, and the frequency in here is dependent on the wavelength. Okay, and that's how the rainbows form. Okay, so again, this picture is not mine, so I have to include the who owns the picture. And this is the bait. This is the main thing in here. Okay, so this is the procedure. So I'm going to click on it. Once I click on it, I'm going to stop sharing the screen and share basically where we are, the link. So let me share that. So when you click on it, it should take you to this page. It's an HTML5 page. I'm in activity, which means that any modern browser should do it for you. Okay. I have it open in here with Microsoft Edge. Microsoft Edge and Chrome are both of the same technology now. Actually, Microsoft Edge uses Chrome too. Okay. Don't bother with the original simulation. This one is fine. So just click on it. Once you click on it, go to the intro. Okay. And this is exactly the picture that you see in the lab. Okay. If you go through the lab, it starts with air and water right now, okay? And you're going to explore the laws of reflection and refraction. Let me check the... It's telling you choose an incident angle between 5 and 85 degrees. The 5 and 85 degrees, so if I take my protractor in here and put it in here, right now it's sitting, I can put it at, what is the angle right now? It has to be at least 5, that's what they say. So this is the angle of incidence in here, about 5 degrees. 85 degrees is somewhere in here. So this is 85 degrees. So you need to put it in this, somewhere in here, okay? So let me turn it off. So that's part of the instructions. Let's see what else the instruction says. So basically, we're going to choose air and water. So the first one is the air and the water in the instructions. I'm looking at the instructions, and I'm supposed to report the index of refraction for the air, which is 1, and that of the water, which is 1.33. So if you look at the table, those are fields you need to enter, okay? And as we change materials, this indices of refraction will change. So if I flip it back, so this will be water and this will be air. So then the indices are backward now. So my beam now is, as you can clearly see, it's fully reflected, okay? There is no refraction whatsoever. If you come from an area that has a high index of refraction compared to a region that has lower index of refraction, at some points, it's going to be refracted. So this is the critical angle, which is clearly about, this is 40, about 50 degrees now, okay? That is your critical angle for this combination. You're going to check on this critical angle. As a matter of fact, it's slightly more than that, around 52 degrees or so, okay? So when you're doing this experiment, you have to be careful in here because it's somewhere above 50 degrees, around 51 degrees or 52 degrees. So again, the default is the way it came in, it comes as water in the bottom and air in the top. So again, let me go back into the instructions. I'm looking at the instructions and let me move the instructions out of the way. So hopefully you guys are following with your instructions. So you plug in the values of the indices of refractions for both air and water. And then you're going to measure the angle of incidence. You're supposed to have 5 trials for the angle of the incidence. So let's say, for example, we start with somewhere around 10 degrees, okay? And we're supposed to find the theta r. So theta r is slightly about 9.5 or something like that, index of refraction in this case, okay? Then I'm going to move it to about 20 degrees. So again, the angle of incidence now is slightly less. It's 19 actually degrees, okay? It should be equal, but it's fine if it's not equal. You can report to the correct values that you have in there. Let's go to 30 degrees, okay? It's again about actually slightly more than 39 degrees. If I go to 40 degrees, so this is the next value. If I go to 50 degrees, try to get some values that are big, okay? Don't go like I did the increments of 10. So I could go 10, 25, 40, that's 3. And then 40 plus, that's about 55 degrees, okay? That's the 4th value. And 55 plus 15, so it's gonna be about 70 degrees, okay? So that's fine, okay? In other words, don't get all the values around 5 degrees. So basically don't move all the values in here, and don't get them all too big either, okay? So try to get them spread as much as possible between 5 and 85, okay? If you make too small of an angle, the error should be big, okay? The errors are actually increasing. Look, I am sitting at about 5 degrees, and the answer is about 4.5. Of course, the half, it's about 10% error. Whereas if I come in here, it's going to be a very tiny error. Okay, it's practically 0 error. Okay, so that is this table. Your theta r calculated should be equal to theta, according to the formula again, theta r is equal to theta a. So in this case, the calculated value should be theta a. The observed value is the one that is going to be measured in here. Once you have that, you find the difference divided by the calculated and times 100 is going to be the percentage error, okay? In other words, is that a match or not? On the next page of the instruction, you're supposed to graph that, okay? Draw the array for at least 2 nominal values, meaning a small value and a big value. So you're supposed to draw the law of reflection in this case. Then we're going to go into the refraction. Again, we're going to stick with this same experiment. We're going to report the values of air and water. So let me stop sharing the screen in there. And let me share with you the instructions so that you're following with me. Share the instructions. So we're done with this part in here. So we're done with this part for the refraction. Now we're going to need to do the refract. So you have a drawing in here for a small value of theta A and a big value. Just focus on the reflected array in this case. Now we're going to do the refraction. Again, we're going to stick with the air and the water to begin with. And the indices of refractions are 1 and 1.333, repeating. And we're going to use Snell's law to find the angle of refraction. Now, you have to be very careful with this part. If you're using a calculator, make sure the calculator is using the proper units, okay? If it is in degrees, that's fine. Make sure that the value that you report in degrees. Sometimes the calculator is set in radians, and you're thinking you're reporting it to degrees, and now you have a mismatch. Because according to this rule in the ruler in here, it's measuring things in radians and degrees. So if you put a degree in the calculator and measuring it in radians, this is the only problem in this lab that I can see that you might run into. And that is not to put the proper units for the angle in here, okay? So if your calculator or putting it on Excel and Excel is giving you radians because Excel can do only radians, make sure you convert the radians to degrees to see that, to degrees to see if there is a match in here between your refracted ray and the reflected one. Again, you're going to have the angle of incidence, 5 values starting from at least around 5 degrees and ending around 85 degrees. And then you're going to calculate using this expression for theta B. Once you have that, we're going to plug the values in here for the calculated ones, and then you're going to look at the observed values. So let me stop sharing again, and let me share with you the screen. So in here, so we're still water and air and water in this order. So we're going to start with something around small value, around 5 degrees. 5 degrees is hard. Let's do 10 degrees, okay? So that's one value. I'm going to measure this angle now. So this is not, this is 10. This is a little over 6 degrees, okay? Around 6 degrees. So I have to be careful in here. So theta B is this angle, and theta A is this angle. Let's go into a big angle in here, around 30, for example. 30, this is 30 degrees, whereas this reading clearly less than 30 degrees, less than 25 degrees, around 20 degrees actually, okay? The reading is around 20 degrees. And let's go to another angle, and because we're supposed to do 5 of them, this is 40, this is 50 degrees. 50 degrees in here, and the angle of incidence, and the angle of reflection and refraction in here. In this case, I have what, 33 or something like that degrees. So again, I'm going to go to 70, 80, and 85. Okay. So now I have all of my readings. I plug in, and then I compare the calculated versus the observed, okay? And the error is going to be in percentage. So you're supposed to do that calculation and find the error between them. And don't forget, you're going to draw 2 refracted beams, okay? Draw the diagram for at least 2 different incident rays. So 1 and a big angle in here, and you will see the different rays, okay? Now we're going to do air and glass. It's the same thing. Instead of air and water, we're going to do the air and glass. So the index of refraction now will change because, let me show you what happened in here, okay? Share. Oops. So we're going to leave air. We're going to change this one to glass. So the index of refraction now is all of a sudden 1 and 1.5. So we're going to follow the same steps as before, okay? And the same drawings. And then we're going to do water and glass. So this is water and glass. The first index of refraction 1.33, and the second one is 1.5, okay? And we do the same steps as before, the same drawings. Now we're going to do water and air. So we keep this one water and change this one to air. Now, we're going to do the same calculations as before. First of all, from this angle, it looks like I have no refraction. I only have reflection, so that we must have exceeded the angle of refraction. So if I do this one, I have to be very careful not to exceed the theta b in here, the critical value in here. Okay? So you have to be careful in here when the upper medium is denser than the lower one, because you might be in a total reflection. So, and then we're going to do glass and air. Glass and air. So again, actually we reach it sooner than before. Okay? And then, so you still need 5 data in this case, even though you have a cutoff in here very close from this point in here. So you still have to vary it somewhere in here because you have 5 cells in here, and do the graphic in here too. And then the glass and the water. Okay, so in this case, we have actually more room for this before we get into the total law of reflection. So at this point in here, so we have more wiggle room. It's the same formula as before. And then we're going to do the internal reflection, the total reflection. So in this case, theta A has to be equal to, let me stop sharing the screen and share with you the instructions. So at this point, we're doing the internal reflection, total internal reflection. So we're still using Snell's law, with the exception now that we need an angle, an incident of angle theta A, so that the angle of reflection needs to be exactly 90 degrees. That means that there is no refraction. Sorry, the angle of refraction needs to be exactly 90 degrees. So that means there is no refraction, because remember, refraction has a finite angle. So if this is 90 degrees, that means it's not there. So if you plug in theta B equals to 0, and then we're going to find an angle that satisfies this condition. So we're going to calculate this one for the glass water. So you have the index of the refraction for the glass, which is supposed to be 1.5. And you have the index of refraction for the air. So 1.5 needs to be in the denominator, because you cannot have an arc sine of something bigger. But 1.3 needs to be in the numerator. So N2 is 1.3 and N1 is 1.5. An arc sine of 1.5 divided by 1.3 gives you a value for theta C. Same thing between glass and the air. The air is 1 and the glass is 1.5. So it's going to give you different in the critical angle in here. And for water to air, so the top one is N1 is water, which is 1.3, and N2 is air, which is 1. So you're going to put in here N1 to be 1.3 and N2 to be 1. And now you have the 3 different values in here. So what you do in this case is you come back to your experiment and you observe the values. So you go back. So for example, this is glass and water. And glass and water is actually the first one in the data that I'm supposed to check. So I have already calculated a value for theta C. All I need to do now is find it. So at this point, it looks like it's this value, 60, 70, 65 degrees, okay? Around 65 degrees, I have reached total reflection. I need to compare the two, experimental and the value that is calculated. Always taking the calculated as to be the true value. Now I'm going to do glass and air. Glass and air. So the angle should be smaller, actually. Okay, I must have reached it somewhere around this point in here. So this is 30, this is 40, this is 50. So it's around 44 degrees, okay? This is the observed value. And the last one, water and air. So this one changes to water. And the angle should be actually somewhere in here, actually, around 51 degrees, okay? And now I compare the two. And there is a question in here, is it possible for it to be less than that of the air? So you're going to look at the observation, the experimentations and answer those questions. It's easy, isn't it? Yes. Very good. All you have to do is make sure you go through the data, you analyze the data. I mean, you do the measurements, be careful with it. And drawing, the drawing is going to be a killer in here. It's going to take you a little bit more time, and use a ruler and please protractor and submit that separately, okay? That's it. That's all your left. You guys don't have any questions? I'm going to stop the recording. No questions? Okay. I'm going to stop the recording. Okay, very good.